Thank you for having me here. What a great stage, what a great audience. I'm Nathan from New York office. I'm going to be talking about graph databases and how to use them. Now, before we get into the details, let's talk about why do we want to use graph databases. I believe most of us have been dealing with graph database here and there, but mostly it's going to be relational database. But some problems are not that obvious that can be solved by relational databases, but some of them are also outright cannot be solved. And that's why we are having this graph databases conversation. So we can give you a new kind of database. So maybe we can use this kind of tool to solve and tackle those problems. Okay. So I've been working with relational database and trying to solve this recommendation engine problem. Right? I believe most of you have seen these kind of statements. People who follow this person also follow those people. People who bought this product also bought those other products. Right? It's clearly a recommendation engine using some relationship discovery kind of algorithm, right? But the statement itself is pretty straightforward. Because we are dealing with a lot of relationship, when we put that into a relational database, there's going to be a lot of join statements. And that is what I've been struggling with lately. Let me explain. People who follow Bob also follow these other people. Right? Let's say I'm following Bob right now. Right now, Ken is also following Bob, as well as Zach and Joe. On the graph, it's pretty straightforward. We know Zach and Joe are our target results. But when we put that into a relational database, things got a little bit trickier. We have to, first of all, create some tables to store all of the data so we can actually work with the data. We have a user table for all the entities, a follow table for all of the relationship. For simplicity, I'll just combine them right now, but that requires some kind of join statements. Now, let's say we are the relational database. Let's try to solve it logically. Right? First of all, we need to find out Bob's follower. Right? How do we do that? Well, we have to do a table scan because we only know about Bob is in the follow column, but the follow column is not indexed. So we have to do a table scan to find out all of the rows that has Bob in the follow column. Good thing right now we only have 4 rows. When we have thousands, tens of thousands, or millions of rows, this kind of scan is going to take a lot longer. Okay? But the second part is much easier. Now we know about Ken is one of the users. As I said before, follow field is not indexed, but the user field is indexed. So we can just apply direct access to find out all the rows that has Ken in the user field. Okay? That part is much more straightforward. Looking at the SQL query, however, is not as intuitive as the graph. Basically, we have to figure out what orientation we have to join these tables together, or what field we need to use to join these tables. Let's take a look at a slightly more complicated scenario. Now we have more mutual relationship. We can ask a slightly different question. Who follows Zach indirectly? So we can recommend Zach to those people. Again, we know about Zach is being followed. So we can traverse these arrows reversely to find out Zach's follower. On the table side, we have to do a scanning, just like before. But at this point, we again have to find out these people's follower. On the graph side, again, we have to traverse through these arrows reversely to find out their followers. On the table side, again, we have to do scanning for each of these users. So as you see, when we add more hops into this problem, we need to add different tiers of scanning. That's going to grow this kind of scan operation exponentially, and the time it takes is going to become unbearable. Okay? But that's not the most complicated problem we have to solve with relational database. For example, when we have a more complex scenario, we are asking us a question: in what way are Alice and Ed are connected? They're located at the diagonal corners of this graph. Okay? So as you can see, we are not only dealing with a single relationship, we are dealing with different kinds of relationship. For example, boss, friend, colleague, marriage, triangles. All of that will require the different table to store all of the data. And then we have to join these tables together to hopefully find a path to go from Alice to Ed. But the problem is, we don't even know what direction this relationship happens, or how many hops, or even what kind of relationship we are looking at. So it becomes a trial and error problem. Imagine how many permutations we have to test in order to get a possible answer going from Alice to Ed. That quickly becomes unmanageable. It would be nice if we can just work with graph. And that's exactly what graph database allow us to do. Looking at the data representation, relational database has tables, graph database has graphs. So we can apply all of those graph logic or algorithms directly to graph database. For example, path finding, node discovery, or shortest path. So we see how powerful a graph database could be. Let's see how we can use it. First of all, we have to create a graph database. And to do that, we have to lay down some fundamental elements. First, we have nodes to store all of the entities. And then, of course, a directional relationship to store all of the relationships. And then we have labels, which are used to tag the nodes. Sometimes we use that to type the nodes as well. Okay. Next, we'll walk through a scenario using Neo4j and Cypher. Neo4j is one of the most well-established graph databases in the market, and it uses Cypher as a querying language. So let's say we are creating this social network using Cypher in our Neo4j graph database. And I only care about part of this graph. So first of all, I'll use this create keyword. First, we'll create these two nodes, Alice and Bob. And this is how we create Alice and Bob in a graph database. Here, Alice is a variable. It's used for pragmatic access. We don't need to add a variable for every single node, but it's nice to have. When we need to use them later, it's pretty easy to just grab it. Next, we have :user. This is basically the label declaration. And then we can add properties to the nodes. Same thing happens to Bob. Next, we want to look at how we create the relationship between them. And we literally just draw the relationship using dashes and arrows. Of course, we can specify the type of relationship, and we can add properties to the relationship. For example, this relationship happens in 2018 and ends in 2019, right? There's a couple months of relationship. It's good, right? But things change, okay? Next, let's say we want to add more business logic in the same space. In this case, we want to capture how users connect to a common activity. So we are adding 2 additional nodes into the space. Notice Ken is not only a user, but also an actor. And of course, we have a Hamilton play. And then, basically, again, we'll draw the relationship between those nodes. So the whole space or whole A graph database is just like a whiteboard, right? We can add a lot of different business logics as they come into our requirement. We don't care about tables. We don't care about types. We just add things into the space. Let's say I want to we want to capture where everybody study at. So I just create a university and then draw the connection between them. Yeah. So now we have a database. Let's look at how we can use this database to query, find out our answers for those questions we had before. People who follow Bob also follow these people. Okay? We saw the SQL versions is not as straightforward as the graph. And then we can see on the right side a cipher version. The first clause is just the match clause. We're basically doing a path matching. So it literally just reads as Bob is being followed by someone who is following someone else. That someone else is who we are looking for. Okay? And then we have who follows Zach indirectly. Don't ask me about that SQL. I gave up after the last one. On the cipher side, however, it's pretty much the same one. As you can see, we locate the first known factor first, which is Zach. Zach is being followed by someone who is also being followed by someone else. And because we are not even limiting the middle node, the end node right there, so we can basically just combine the two follow relationship as follow times 2. So we can quickly just scale into 3 hops, 4 hops relationship. Again, back to our complex scenario, we want to find out in what way Alice and Ed are connected. Again, we only know about Alice and Ed. We don't know about the direction, type, or number of hops of the relationship between them. So we basically just locate the starting node and ending node, and then draw the relationship between them. In this case, I limit the number of hops for optimization reason. And then after we get all of those paths, we can just apply this relationship function to those paths to find out every single relationship within each path. Or let's say I only want a single path, I can just apply this shortest path function to get one single path out of it. So you can see the graph database is pretty powerful to solve specific kind of problem. We can take a look at how other users are using this graph database. Of course, all of those tech giants are using some form of graph calculation in one form or another. But there's a whole another suite of problems that are not very obvious can be solved by graph database. For example, design a system that can find the conversion rate between any 2 length units. Let's say I'm trying to convert centimeters to meters. That conversion rate is pretty straightforward, it's 100. Right? But in some cases, this conversion rate is not very straightforward. Right? For example, I want to convert from centimeters to light year. Most of us won't have that memorized. So most of the time, we will convert centimeters to meters first, and then kilometers, eventually light year. But that's not the single path we can take. We can also convert centimeters to yards, to miles, eventually light year. So that becomes a path-finding problem. But because we're dealing with path-finding problem, we can basically just chuck that into a graph database. In this case, every single node is a unit. The relationship connecting them is the conversion rate. So we can just find a possible path and get all of those relationships to connect this path and multiply them together to get our answer. Pretty straightforward. So now we identify some problem that can be solved by graph databases. Let's talk about some risk we encounter when we use graph database in an actual project. More likely than not, when you have a project already running, a relational database is probably set in place to store all of the transactional data. Now, you probably also encounter some problems that are ideal for graph database. So, in this case, we have two separate systems to store data. One is the main database, contains all of the transactional data. The other one is the graph database to contain intermediate data. We are not using graph database to store as our main data storage because graph database has a lot of overhead to make all of those graph algorithm native and easy to use. To support those things, of course, we are gonna add a lot of pointers and memories to put in the slots. Okay, so now we have two systems together. First problem we will encounter is data transformation and migration. We basically have to move some of the existing data from relational database to graph database so we can apply those graph algorithms. Okay. One thing we can tackle this problem is Data Forge. Data Forge is a library that's optimized for doing data transformation, and it can streamline all of the different kinds of transformation from one format to another, or data wrangling. Okay. Next, we have keeping data in sync. That's a problem that most of us have been dealing with in our regular projects. When we have multiple systems, we try to make sure there's only one source of truth. Okay. There are different ways to deal with that. For example, schedule jobs to sync the data periodically, or have a event-driven model. Okay. I won't go too deep into detail on that one. Last is result egress. So after we query the graph database, we get our answers. But that kind of answer is probably pretty busted. When I say busted, I mean bolted. Right? We have probably not just a couple of the recommendations, we have tens of thousands of recommendations. We probably want to apply some more analytics to those answers, right? So to do that, it would be ideal to migrate these kind of results back to a table-based data storage. And that is, again, our data transformation and migration problem. Of course, there are different tools to handle that kind of thing. Data Forge is one thing. Actually, graph database has been around for quite a while, probably more than 10 years. So there are a lot of tools exist, either first party from Neo4j or different graph databases, or from the community. So there are a lot of tools out there to solve different kinds of problems. These are the three major ones, and a lot of people have solved that already. So hopefully, after this talk, we can start thinking about problems in a slightly different perspective and having more options other than relational database. Thank you very much.